that in order for this, you need to have, you might associate incorrectly this with this and this with this, so that could be one possible mistake. But the basic idea is simple. Somehow you need to find out how to propagate the error to the output. And so for a multiplexer, it's actually straightforward. But which is just an example to show that you can apply the algorithm at different levels. You can apply it at the functional block level. You can actually apply it at the lower level. People have applied the algorithm to the transistor level. But the basic idea is still the same, what we have seen. Any other questions on that quiz? Now, as one of you have already done the feedback module, the homework, and actually I haven't checked it, so I can't say if this is correct. Some of the questions may take some time.
I had a question with the feedback module. Should I reach in the office hours? I have a general question, I think.
Okay, so is it a question about clarification or?
Clarification, as in what I'm supposed to be doing.
Okay, so what is the question?
It's question number 2.
Okay.
It says it has a table, it has a truth table.
Right.
It says construct a combinatorial circuit, which is non-redundant. So I'm not sure what that meant.
Oh, so you are given a truth table, and you have to come up with a combinational circuit which is not redundant. I see.
Non-redundant.
So you have to come up with a non-redundant combinational circuit. Yeah, that's what people usually do. That usually is you consider what you do is non-redundant.
Okay.
Yeah, basically, so you should not have any redundant terms in it. Now, sometimes the question can be, come up with a implementation which is redundant. And in that case, you have to create a redundant term, which is still correct, so it will still work correctly, but it will introduce a redundancy. And as a result of the redundancy, there could be some untestable faults in it. But in this case, if the question is to come up with a non-redundant implementation, that is what you usually do with Carnot maps.
Okay.
So that's a usual thing.
Okay.
Well, I guess maybe I should add something more. Sometimes if you are designing asynchronous, so have you been involved in designing asynchronous circuits?
Yeah, I did.
Okay, so in asynchronous circuits, sometimes the redundancy is intentional. So sometimes if you don't include a redundant term, then there's a possibility of a glitch. And a glitch doesn't have any significance in a synchronous sequential circuit because you wait for all these things, all the transitions to settle down before you sample. But in case of an asynchronous circuit, there is no synchronization mechanism, and your glitch could trigger something. So in case of an asynchronous circuit, sometimes redundancy is actually intentional. But in most cases, unless you are some asynchronous circuits are used only in some rather special circumstances. I think for some design of some very high-speed sequential circuits, asynchronous circuits are used because the asynchronous circuits, they tend to be unstable. There's no synchronization mechanism, so sometimes their behavior is not predictable, so they are not used that often. And I don't know if I mentioned that there was a secret project at Intel where they tried to look at the idea of designing a microprocessor without any synchronizing clock. So they said, okay, if we can cleverly design it and get rid of the clock and somehow make it run, then that will save time, because whenever you insert clock, you are introducing some delays there. And well, it turned out they couldn't get it to work. So there was a team at Intel, they had a presentation in a workshop that I attended. And the reason they presented the work, because they had already, I guess, given up. So, because they didn't feel the need to keep it secret anymore. So, but that's an intriguing idea, asynchronous circuits. People keep coming back to it. And who knows, maybe somebody might come up with some clever way of making them work. But so far, that hasn't happened. Okay, so let's look at mission time, which is another reliability measure. Now, mission time is used for very high reliability systems. Now, you would not use this metric, you would not use this measure to measure a reliability of a microwave oven. When it stops working, you go and buy another one for maybe 50 bucks. But let us say if you have a critical system, maybe if you have a life support system, if you have a autopilot of a plane, then you want to make sure that the inherent reliability of the system never goes down below a certain level. And that is mission time. So basically the idea is that reliability during the mission whatever the mission is. So let us say for a plane it could be maybe a duration of the flight. For the autopilot system, reliability during the mission must remain above a certain threshold. And let's assume that the threshold reliability is called R sub TH. So mission time is basically defined in this way, that is such that the reliability at the, did I say uppercase, at mission time, let's call it T sub m, is greater than or equal to the threshold reliability. So during the mission time, the reliability is above some threshold, and RTH would be chosen depending on the particular application. Maybe perhaps, I don't know, 0.95% or so. It would depend on your requirements. In some cases, you would not want your reliability to drop below 99%, or in some cases, maybe you may allow it to go down to 85%. So that may depend on application, but it may be like 0.95%. Now this is a strict measure. And let me illustrate this using a diagram. Now, as I was mentioning, reliability decays with time for relative to permanent failures. So here we have time. And initially, we often assume that the reliability is 1, when we start. And let's assume that reliability drops in this way. And let us say here is that, let's assume that RTH is 0.95. So here is RTH. And so the time during which reliability is above or equal to RTH is your mission time. Now this is something that you would use only for very high reliability missions. Okay, now let us look at two cases. Now these are the basic cases. And first we are going to consider a system which is subject to permanent failures. And next we are going to consider a system which is subject to temporary failures. And now, for a system subject to permanent failure, now in both cases we are going to model them as a Markov model, but let me mention about something. Let us assume a single system which is subject to permanent failures. Okay, so we are considering single unit. Subject to permanent failures. So basically, once the permanent failure occurs, we throw it away. That's what we mean by this. And let me mention about an assumption, the constant failure rate assumption. Now in this class we will generally use this assumption. We assume that the failure rate is constant. And advantage is that it keeps the analysis simple. And it may be true during operational life. Maybe a good approximation. Now let us look at the classical bathtub curve. The bathtub curve, I should mention, it is a rather controversial idea, and I will mention why it is. The idea is that failure rate of a typical unit, here's the failure rate, actually I was looking at some of the videos, and I think maybe I should stop being very close to this edge.
Why not?
Because when we have more of this white, then it adjusts automatically to the overall available light and sends it, so it adjusts it assuming that this white was part of the whole thing, whereas actually we want to focus mostly on this blackboard part. You don't agree?
No.
I don't know if I read that.
Okay, maybe we'll look at that.